If you think about the most powerful engine you can imagine, a rocket launching into space, a Formula One car screaming down the track, they all have something in common. No matter how perfectly we engineer them, they all hit a wall. They can't get past this fundamental speed limit that's just built into the universe. So today, we're going to figure out what that limit is. We're going to go on a journey from the machines we can see and touch all the way down to the invisible, chaotic dance of molecules that's secretly running the whole show. And that brings us to the big question, right? Why can't we build that perfect 100% efficient machine? I mean, where does all that wasted energy actually go? Well, it turns out this isn't really an engineering problem at all. It's a law of physics. This idea of a perfect engine is nothing new. For centuries, scientists and engineers have been chasing this ghost, trying to find the absolute maximum efficiency for using energy. And they found out that the limit isn't set by our tools or materials, but by the fundamental rules of reality itself. And the first person to really nail this down was a French engineer named Sadi Carnot. His theorem is actually pretty simple and elegant. It says that for any two temperatures, a hot source like burning fuel and a cold sink like the outside air, there is a maximum possible efficiency. It's a hard ceiling, and no real-world engine can ever beat it. Okay, but how do we know for sure that this limit is real? Well, it all comes down to a really clever thought experiment. Let's just imagine for a second that we did build a super efficient engine. We'll call it Engine A. And let's say we use its power to run a normal, standard engine, Engine B, but we run it completely backwards, so it acts like a heat pump or a refrigerator. All right, follow the logic here, because this is cool. So we start by assuming our Engine A is more efficient. That means it produces some extra work, right? We then take that extra work and use it to power Engine B backwards. And here's where it gets really weird. The combined machine, this Engine A plus Engine B setup, would start pulling heat from a cold place and dumping it into a hot place, all on its own, with no plug in the wall, no extra power needed. And that just can't happen, ever. It would be like seeing a puddle of water freeze solid on a hot summer day. It completely violates one of the most basic rules of the universe, the second law of thermodynamics. So if our conclusion is impossible, that means our starting assumption had to be wrong. A super efficient engine can't exist. There really is an unbreakable limit. So we've established there is a limit, but why? Why can't heat just decide to flow from a cold thing to a hot thing on its own? The reason is tied to a much deeper, more fundamental idea that really governs everything, and it has a name: entropy. So what is entropy? Well, in the simplest terms, it's just a measure of disorder or randomness. It's the reason a neat stack of papers tends to get messy over time, and why a broken egg will never, ever spontaneously put itself back together. It's also a way of measuring how much of the energy in a system is so spread out and disorganized that you just can't use it to do anything useful anymore. And this really shows the huge gap between a perfect theory and messy reality. You see, in some perfect, frictionless theoretical world, physicists call this a reversible process. The total amount of entropy would stay the same. But here in the real world, every single action, every bit of friction, every bit of heat that's lost, it's all irreversible. And with every single one of those irreversible actions, the total disorder of the universe goes up, just a tiny little bit. It's a one-way street, and the traffic is always heading towards more disorder. Now, I know these big cosmic laws can feel a little bit like magic, but they're not. They're really just the large-scale consequence of trillions and trillions of tiny particles bouncing around. So it's time to zoom way in and meet the molecules. Yeah, you see, thermodynamics isn't some kind of top-down command from the universe. It's what naturally emerges from the statistical dance of countless tiny particles. The laws that govern our engines are really just the laws of huge numbers, all applied to the behavior of molecules. To really get a handle on this molecular dance, we first need to understand all the different ways a single molecule can move around and hold onto energy. And this brings us to a neat idea called degrees of freedom. Now, there's this law that's, it's surprisingly fair. It's called the law of equipartition of energy. And it basically says that when you pump energy into a system of molecules, that energy gets shared out equally among every possible way those molecules can move, rotate, or vibrate. You can think of it like a budget. Every single degree of freedom gets an equal slice of the energy pie. So let's start with the simplest possible case, a single atom of a gas like helium. Just picture it as a tiny billiard ball floating in space. It can only really do three things. It can move up and down, left and right, and forward and back. That's it. So we say it has 3 degrees of freedom. Okay, now let's make it a little more complex. Let's look at a diatomic molecule, like the nitrogen that makes up almost 80% of the air we're breathing right now. It's basically 2 atoms stuck together, like a tiny dumbbell. Now, it can still move in those 3 directions like the helium atom, but it can also tumble end over end in 2 different ways. So 3 plus 2, that gives it a total of 5 degrees of freedom. And you can probably see the pattern here. If you have a more complex, bent molecule like water, H2O, it can spin around all 3 axes, like a little toy airplane. So you get the same 3 ways to move, plus 3 different ways to spin, for a grand total of 6 degrees of freedom. The big takeaway is simple. The more complex a molecule's shape is, the more ways it has to hold and store energy. And here is the payoff. This isn't just some abstract theory. This table shows a direct, measurable link between the microscopic world of molecular shapes and the macroscopic world we can actually measure. You can see right here, the more degrees of freedom a gas's molecules have, the lower its specific heat ratio is. And that number is absolutely critical when you're doing the math to calculate an engine's efficiency. It all connects. Okay, so we've seen how individual molecules can move and spin. But what happens when you get trillions of them all bouncing off each other inside a container? What does their collective speed look like? I mean, it's just pure chaos in there, right? Molecules are colliding with each other billions of times a second. So you might think they'd all eventually settle down and move at roughly the same average speed. But do they? No, not at all. In fact, something much more amazing happens. Out of all that complete and utter randomness, a perfectly predictable pattern emerges. This graph is called the Maxwell distribution, and it shows us that while a few molecules are moving super slow and a few are going incredibly fast, the vast majority of them are all clustered right around a most probable speed. It is beautiful statistical order born from pure chaos. So now that we've seen the messy, chaotic, statistical truth of what's happening in the molecular world, let's zoom back out. Let's use that newfound knowledge to upgrade our understanding of the big picture. The basic gas laws that we often learn in school, like the famous ideal gas law, they work pretty well, but they make a couple of big, simplifying assumptions. They basically pretend that molecules are just mathematical points with no size and that they don't interact with each other at all. But of course, we know that's not true. Real molecules take up space, and they have tiny forces of attraction between them. And this is where the amazing van der Waals equation comes in. You can think of it as a beautiful upgrade to that older, simpler model. It adds 2 very clever correction factors. The B term accounts for the actual volume the molecules themselves take up, and the A term accounts for that subtle attraction between them. With just those 2 little tweaks, our theory gets a whole lot closer to matching reality. So what's the big idea at the end of all this? From the absolute limit of a massive engine all the way down to the speed of a single tiny molecule, we keep finding the same incredible pattern, simple, predictable, even beautiful laws emerging from what looks like total chaos. And it really makes you wonder, doesn't it? What other incredibly complex systems, like the global economy, or the Earth's climate, or even how our own brains work, are just following hidden statistical rules that we just haven't discovered yet?